now, more than 15 billion miles from the nearest source of warmth, a machine the size of a small car is drifting through the coldest, emptiest, most hostile environments ever directly measured by human technology. It weighs about 722 kilograms. Its main antenna is 12 feet across. Its body is roughly the size of a compact car with a long boom extending outward. It runs on power generated by decaying plutonium, and that power supply has been losing about 4 watts every year for nearly half a century. The computer at its core processes roughly 8,000 instructions per second. A modern smartphone processes more than 14 billion. It was designed to study Jupiter and Saturn. It was expected to function for 5 years. It has been operating for 47 years, and it is still talking to us, from a place no human object has ever been before, from a place that, until very recently, we had no direct evidence of at all. Its name is Voyager 1, and what it found after crossing 15 billion miles of space is something that should change how every person alive thinks about where they are, what protects them, and how fragile that protection actually is. But to understand what it found, you first need to understand what it crossed. Voyager 1 launched on September 5th, 1977 from Launch Complex 41 at Cape Canaveral, Florida. A Titan III AE Centaur rocket carried it through Earth's atmosphere and set it on a trajectory toward the outer planets. Its twin spacecraft, Voyager 2, had actually launched 16 days earlier on August 20th, but on a slower, a more sweeping path that would carry it past all 4 of the outer gas giants. Voyager 1 took a faster, more direct route, swinging past Jupiter in March of 1979 and Saturn in November of 1980. At Jupiter, Voyager 1 discovered active volcanoes on Io, the innermost of Jupiter's large moons. It photographed the Great Red Spot in detail no human instrument had ever captured before. It imaged Ganymede and Callisto and Europa with enough resolution to reveal surfaces that had only been points of light in every telescope that had ever looked at them. At Saturn, it studied the ring system with an intricacy that previous missions had only hinted at. It made the first close observations of Titan, Saturn's largest moon, and found an orange haze thick enough to obscure the surface entirely, a result that would shape decades of planetary science that followed. Then its planetary mission was effectively over. It had done what it was sent to do. But Voyager 1 kept going. There was nothing to stop it. The gravitational assist from Saturn had flung the spacecraft upward out of the plane of the solar system's planets, heading away from the Sun at approximately 38,000 miles per hour. No engine fired to slow it down. No course correction aimed it at a new destination. Gravity and engineering had prescribed a trajectory, and Voyager followed it. Outward, second by second, mile by mile, year after year. Voyager 2 followed a different path, but the same ultimate fate. After completing the only mission in history to visit all 4 outer planets, Voyager 2 also headed outward, angled southward relative to the plane of the solar system. By the late 1980s, both spacecraft had completed their planetary work and entered what NASA designated the Voyager Interstellar mission. The new objective was simple in concept and staggering in ambition. Keep flying, keep measuring, find the edge of the Sun's influence and tell us what lies beyond. The distances involved resist easy comprehension. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Voyager 1 is currently more than 163 astronomical units from the Sun. Multiply 93 million by 163. The result is over 15 billion miles. Voyager 2 trails at approximately 140 astronomical units. and both spacecraft continue moving outward at speeds that would cross the entire continental United States in under 5 minutes, and that speed barely registers against the scale of interstellar distance. From Voyager 1's current position, the Sun would appear as a very bright star, not a disk, not the blazing source of warmth and light that dominates our sky, a point of light. Perhaps the brightest point in its sky, but a point nonetheless. The warmth is gone. The solar wind, the stream of charged particles that had accompanied the spacecraft every moment of its 47-year journey, has ended. That wind ended. That is the story. But Voyager 1 does not fly alone in the hierarchy of human exploration. There were others that ventured outward before it, and an understanding what happened to them clarifies exactly what kind of category Voyager now occupies. Pioneer 10 and Pioneer 11 were launched in the early 1970s, preceding the Voyagers into deep space. Both spacecraft made crucial contributions. Pioneer 10 was the first spacecraft to pass through the asteroid belt and travel to Jupiter. Pioneer 11 was the first to visit Saturn. Together, they opened the outer solar system to human instruments, but Pioneer 10 sent its last detectable signal in January of 2003, more than 2 years before Voyager 1 crossed the termination shock, the innermost boundary of the heliosphere's edge region. Pioneer 11 fell silent even earlier, in September of 1995. Both spacecraft are still out there, drifting through space, but they are mute. They carry no functioning instruments, they send no data, and they have become inert metal, tumbling through the void, objects rather than instruments, artifacts rather than explorers, New Horizons, the spacecraft that flew past Pluto in July of 2015 and later made the first close visit to an object in the Kuiper Belt, called Arrokoth, in January of 2019, remains active and is heading outward. But it sits at roughly 60 astronomical units from the Sun. It has not yet approached the termination shock. It will be decades before New Horizons reaches the boundary region, and its instruments were not designed to characterize the interstellar medium with the same approach as the Voyagers. The Voyagers occupy a category that contains only themselves. They are the only machines in human history that have physically entered the medium between the stars and sent back measurements of what they found there. In 2025, that mission is entering its final phase. NASA turned off Voyager 1's cosmic ray subsystem on February 25th of this year, conserving the remaining power. 3 science instruments continue to operate. Engineers at JPL believe the spacecraft may retain enough electrical power to keep at least one instrument alive into the 2030s, drawing on the slowly declining output of its radioisotope thermoelectric generators. Each year, those generators lose approximately 4 more watts. What was 470 watts at launch is now approximately 220. A signal from Earth takes more than 23 hours to reach Voyager 1. The reply takes another 23 hours to return. A single exchange requires nearly 2 full days of waiting. This is what we built. This is how far it went. And the place it entered, the place beyond the bubble, is the subject of everything that follows. But before you can understand what Voyager crossed, you need to understand what the heliosphere actually is. Not the textbook summary, not the diagram in a science classroom. The real thing in all its complexity and scale, because the heliosphere is not just a boundary on a chart. It is the reason anything complicated has ever existed in this solar system. It is the reason you are here. Section 2. The Bubble. What the Sun built without telling us. Every second, without pause, without any possibility of being switched off, the Sun is losing mass. Not through the nuclear fusion that powers its light and heat, and though that process converts 4 million tons of matter into pure energy every single second. What concerns us here is a different kind of loss entirely. the Sun also loses approximately 1.5 million tons of material every second through a completely separate mechanism. This material does not become energy. It does not vanish. It leaves. It physically departs the Sun's surface and races outward into space as a continuous stream of charged particles, protons and electrons and heavier ions, stripped from the solar atmosphere and flung outward in every direction at speeds ranging from 300 to 800 kilometers per second. This is the solar wind. It is the single most important factor protecting every object in our solar system from the full hostility of the galaxy beyond, and it begins in a layer of the Sun's atmosphere called the corona, which presents one of the most enduring puzzles in all of solar physics. The visible surface of the Sun, the photosphere, has a temperature of roughly 5,800 Kelvin. That is hot by any human standard, but it is a number that makes physical sense in the context of nuclear fusion happening just below it. The corona, the outermost layer of the Sun's atmosphere, lies above the surface, and somehow moving away from the heat source, the temperature does not drop. It rises dramatically. The corona reaches temperatures exceeding 1 million Kelvin. Some regions exceed 3 million. This is like walking away from a campfire and finding that the air 10 feet away is 1,000 times hotter than the flames themselves. It violates simple physical intuition. Scientists have proposed various mechanisms to explain coronal heating, including magnetic reconnection events called nanoflares, where small magnetic structures on the solar surface snap and reconnect, releasing bursts of energy that heat the surrounding plasma. Another proposal involves the dissipation of magnetohydrodynamic waves propagating upward from the solar interior, transferring energy into the corona through electromagnetic interaction. The precise balance of these processes remains an active area of research. Parker Solar Probe, launched in 2018 and designed to fly closer to the Sun than any previous spacecraft, has been gathering direct measurements of the corona that are still being analysed. But the consequence of the corona's extreme temperature is settled fact regardless of its course. At 1 million degrees and above, the thermal energy of coronal particles exceeds the gravitational binding energy at the Sun's surface. The Sun cannot hold onto its own atmosphere. Protons and electrons stream outward in a supersonic flow that never stops. Eugene Parker, a physicist at the University of Chicago, predicted the existence of this solar wind in 1958. His paper was initially rejected by reviewers who considered the idea implausible. The editor overrode them and published it. Within 4 years, spacecraft had directly confirmed what Parker had calculated. The solar wind is real. It blows continuously, and the structure it creates is the largest single thing in the solar system. The wind is not uniform. It emerges faster from coronal holes, regions where the Sun's magnetic field lines open directly outward into space, rather than looping back to the solar surface. The fast wind from coronal holes can exceed 700 kilometers per second. The slower wind from regions of closed magnetic loops averages around 300 to 400 kilometers per second. Both carry with them the Sun's magnetic field, frozen into the plasma by the high electrical conductivity of the ionized gas. As the Sun rotates, roughly once every 27 days at its equator, these embedded magnetic field lines get wound into a vast spiral pattern extending outward through the entire solar system. This structure is called the Parker spiral, and it is the skeleton of everything that follows. Every planet, every moon, every asteroid, every comet, every grain of interplanetary dust in our solar system exists within this spiraling magnetic web. It is the Sun's influence made physical, a magnetic architecture that fills the space between the planets and extends far beyond any of them. The wind carries this structure outward. It takes the solar wind roughly 4 days to travel from the Sun to Earth, about 2 weeks to reach Jupiter, About 4 months to reach Neptune, and it keeps going, past the Kuiper Belt, past the scattered disk of icy bodies beyond Neptune, growing thinner and colder as it spreads across an ever larger volume, until something stops it. What stops it is the interstellar medium. The space between stars is not truly empty. It contains a thin but measurable population of gas and dust, threaded by a magnetic field of galactic origin. This material exerts pressure. Not much pressure by any standard a human body would register, but enough to matter across the enormous distances of the solar system's outer regions. The interstellar medium pushes inward against the solar wind from all directions. The solar wind pushes outward. Where these two pressures balance, a boundary forms. That boundary, the outer edge of the sun's physical influence on its surrounding environment, is called the heliopause, and everything between the sun and the heliopause is the heliosphere. To understand the structure of this bubble, it helps to move through it outward from the sun, layer by layer, the way Voyager did. The solar wind leaves the corona at supersonic speed, meaning it travels faster than the speed at which pressure disturbances can propagate through the surrounding medium. It flows outward through the inner solar system, through the orbits of the inner planets, past Earth, past Mars, past the asteroid belt, past Jupiter, past Saturn, past Uranus, past Neptune. Over this entire distance, the wind remains supersonic. It is still outrunning its own pressure waves. It is still flowing freely. Then at roughly 80 to 100 astronomical units from the Sun, depending on solar activity and local conditions in the interstellar medium, the wind hits something. The inward pressure of the interstellar medium has been building. The solar wind, spread across a vast sphere and thinned accordingly, can no longer outrun the pressure bearing in on it from outside. The wind abruptly decelerates from supersonic to subsonic speeds. This transition point is called the termination shock, and the word shock is precise here. This is not a gradual slowing. It is an abrupt, turbulent deceleration, like air piling up in front of a blunt object moving at supersonic speed. The kinetic energy of the solar wind converts into thermal energy. Temperatures in the post-shock region can exceed 100,000 Kelvin. The wind does not stop. It slows, compresses and heats. Voyager 1 crossed the termination shock in December of 2004 at a distance of approximately 94 astronomical units from the Sun. This was itself a significant discovery. The crossing had been predicted, but the precise distance was uncertain before Voyager arrived. 94 astronomical units placed the termination shock farther than some models had predicted, and closer than others. The shock was not a smooth, symmetric shell. It was an uneven, a fluctuating surface, and Voyager passed through multiple times as the boundary rippled back and forth across the spacecraft's position. Voyager 2 crossed the termination shock in August of 2007 at a distance of approximately 84 astronomical units, 10 astronomical units closer to the Sun than its twins crossing. This asymmetry was not random. The solar system is moving through the local interstellar medium at roughly 23 kilometers per second in the direction of the constellation Hercules. The interstellar medium flows against the heliosphere from that direction, compressing the boundary closer to the Sun on the side facing the direction of motion and allowing it to extend further on the trailing side. The heliosphere is not a perfect sphere. It is a dynamic asymmetric structure, its shape determined by the interaction between the solar wind and the medium it ploughs through. Voyager 1 exited on the upstream side of this structure. Voyager 2 crossed the flank. The different crossing distances confirm directly, for the first time, that the heliosphere's shape varies significantly depending on where you cross it. Beyond the termination shock lies the heliosheath. This is the thick buffer zone between the termination shock and the heliopause. Here, the decelerated solar wind piles up in a turbulent, magnetically complex region that may extend 30 to 50 additional astronomical units outward. The heliosheath proved far stranger than anticipated. The magnetic field within it was chaotic, and with field lines folding back on themselves and forming magnetic bubbles that trapped and released energetic particles unpredictably. Temperatures remained elevated in the hundreds of thousands of Kelvin as the kinetic energy of the decelerated wind continued to diffuse through the turbulent plasma. The heliosheath was a zone of transition, neither fully solar nor fully interstellar, a no man's land where two vast physical systems pressed against each other. And at the outer edge of the heliosheath, the heliopause, this is where the solar wind stops flowing entirely. This is where the sun's magnetic domain ends and the galaxy's begins. This is the point beyond which the sun can no longer influence the local environments in any direct physical way. Everything inside the heliopause exists within the sun's protective influence, but everything outside exists in conditions shaped entirely by the galaxy. The heliosphere is not a perfect sphere. Boston University astrophysicist Merav Ofer, who directs NASA's SHIELD Research Center, has proposed based on her modelling that the heliosphere is shaped more like a croissant than the traditional comet shape with a long tail, a structure where the interstellar magnetic field bends the solar wind back on itself in a way that creates lobes on either side. Whether it resembles a comet, a croissant, or something in between remains an active area of research. What is not in dispute is the core fact. The heliosphere is a dynamic, asymmetric, three-dimensional structure that varies in size and shape depending on solar activity, the local density of the interstellar medium, time and the direction of the solar system's motion through the galaxy. What this bubble does is the most important part. The galaxy is saturated with cosmic rays. These are not electromagnetic radiation like visible light or X-rays. They are physical particles, mostly protons but also helium nuclei and heavier atomic nuclei and electrons, travelling at velocities that approach the speed of light. They originate from the most violent processes in the Milky Way. Supernova remnants are the primary source. When a massive star exhausts its fuel and explodes, the expanding shock wave accelerates charged particles trapped in the turbulent magnetic fields at the shock front through a process called diffusive shock acceleration, where particles bounce back and forth across the boundary, gaining energy with each crossing over thousands of years. The pulsars, the rapidly spinning neutron stars left behind after certain supernovae, generate intense rotating magnetic fields that accelerate particles in their magnetospheres. Binary star systems where material transfers between companions produce shocks capable of additional acceleration. These particles arrive from everywhere, at all times, in an isotropic rain that does not pause, does not vary with the time of day or the season, and has been falling for as long as the galaxy has existed in its current form. The heliosphere blocks the majority of them from reaching the inner solar system. The shielding mechanism is electromagnetic. Galactic cosmic rays are electrically charged particles. When a charged particle enters a magnetic field, it experiences a force perpendicular to both its velocity and the field direction, and this force curves the particle's path. In the complex, turbulent magnetic environment of the heliosphere, incoming cosmic rays encounter a constantly shifting maze of magnetic field lines carried outward by the solar wind. Lower energy cosmic rays, which have smaller momentum and are more easily deflected, get scattered repeatedly. Their paths become randomized. Many are turned around entirely, reflected back into interstellar space before they reach the inner solar system. The effectiveness of this shielding varies with the solar cycle. During solar maximum, when the sun is most active, the solar wind is stronger. The magnetic field embedded in it is more intense, and the heliosphere inflates slightly. Cosmic ray suppression increases. The flux of galactic cosmic rays reaching the inner solar system measurably drops. Yet during solar minimum, the wind weakens. The magnetic field becomes more orderly and less effective at scattering particles, and more cosmic rays penetrate inward. This 11-year oscillation in cosmic ray intensity is one of the most reliably measured phenomena in space physics, tracked continuously for more than 70 years by ground-based neutron monitors and space-based detectors. Estimates based on modelling and direct measurements indicate that the heliosphere reduces the galactic cosmic ray flux, reaching the inner solar system by approximately 75% compared to the unshielded interstellar value. Only about 25% penetrates to the vicinity of Earth. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is even more dramatic, at reducing the flux by factors of 5 to 10 or more. This is not a minor effect. It is the difference between a radiation environment that permits the existence of complex chemistry, stable DNA, and biological evolution, and one that systematically erodes them. Earth has a second layer of protection, on top of the heliosphere shielding. Its own magnetic field, the magnetosphere, deflects additional charged particles. Astronauts aboard the International Space Station, which orbits within both Earth's magnetosphere and the heliosphere, receive a radiation dose roughly 10 times higher than the average person on Earth's surface, primarily from trapped radiation in the Van Allen belts and the fraction of galactic cosmic rays that penetrate both the heliosphere and the magnetosphere even under normal conditions. Even this modest cosmic ray exposure is carefully tracked and limited by mission duration constraints. Beyond low Earth orbit, beyond the magnetosphere, the full heliospheric environment applies. Beyond the heliopause, there is no heliosphere left to help. The bubble exists. It has existed for the entire 4.5 billion years of Earth's history, in some form at some size, because the sun has been exhaling continuously for all of that time. Every species that has ever existed on Earth, every ecosystem, every strand of DNA that has ever replicated, every organism from the simplest single-celled life to everything alive today has existed within the heliosphere's protection. And most people have never heard of it. Let's be more precise about the scale of what that means, because the numbers involved in the heliosphere's construction are not the kind that fit easily into everyday intuition. The solar wind deposits enormous amounts of energy into the surrounding medium. At Earth's distance, the solar wind carries an energy flux of roughly 1/1,000,000th of the total solar output, which sounds modest until you consider that the total solar output is approximately 3.8 times 10 to the 26th watts. The portion that goes into the solar wind is still enough to inflate a bubble extending more than 100 astronomical units in every direction, a structure with a diameter larger than the distance from the inner solar system to the termination shock in every direction simultaneously. The heliosphere is, by volume, the largest single structure associated with our Sun, larger than the Sun itself by many orders of magnitude, larger than the orbits of all the planets combined, larger than the Kuiper Belt, larger than the scattered disk. The heliosphere contains all of these within it, and then extends beyond all of them into the region where the solar wind begins to fail. The termination shock, where the solar wind first slows from supersonic to subsonic speed, sits at roughly 80 to 100 astronomical units. Neptune, the outermost of the 8 recognized planets, orbits at about 30 astronomical units. The termination shock is 3 times farther out than Neptune. The heliosheath, the turbulent buffer zone between the termination shock and the heliopause, extends another 30 to 50 astronomical units beyond that. The heliopause, the actual edge of the bubble, he sits at approximately 120 astronomical units in the upstream direction. That is 120 times the distance from Earth to the Sun. Beyond 120 astronomical units lies what Voyager measured and what we have been describing. But there is an important distinction that news headlines often blur, one that the reference script mentioned at the outset, and that deserves clear articulation. The heliosphere is not the same thing as the solar system. The solar system, defined by the Sun's gravitational dominance, extends enormously further than the heliosphere. The Oort cloud, a vast theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to begin at roughly 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. Voyager 1 at 163 astronomical units has not even reached the inner edge of this structure. At its current speed, it would take approximately 500 years to arrive at the Oort cloud's inner boundary, and roughly 30,000 years to pass through the cloud entirely. By the definition of gravitational dominance, Voyager is still very much inside the solar system, and will be for tens of thousands of years. What it crossed was not the solar system's edge. What it crossed was the Sun's magnetic and plasma domain, the region where the Sun's direct physical output actively shapes the local environment. Inside that domain, solar wind, solar magnetic field, solar particle populations. Outside that domain, galactic magnetic field, galactic cosmic ray populations, interstellar plasma. Both regions remain within the gravitational reach of the Sun, but they are physically, electromagnetically, and in terms of their particle environments, completely different places. This distinction matters because it clarifies what the heliosphere actually is. It is not the solar system's outer edge. It is the Sun's zone of active environmental influence, a sphere of dominance maintained moment by moment by the solar wind's continuous outflow. It is, in this sense, dynamic rather than static, a maintained condition rather than a fixed structure. If the Sun stopped producing a solar wind, the heliosphere would collapse. It does not persist on its own. It is the consequence of ongoing solar activity applied continuously over time. The heliosphere is the Sun's breath, held outward against the pressure of the galaxy. It takes that breath roughly a year to reach the termination shock, travelling at the solar wind's speeds. It takes somewhat longer as the decelerated wind navigates the heliosheath to reach the heliopause. The Sun's influence in this physical sense extends outward on a timescale of years rather than the instantaneous presence its gravitational field implies. A change in the solar wind today will take months to reach the outer heliosphere and years to affect the position of the heliopause. The bubble breathes slowly, on timescales of years at the boundaries, responding to the Sun's activity cycle with a lag that reflects the light travel time equivalent of over a day and a half to the heliopause. There is one more feature of the heliosphere that the Voyager crossings revealed, one that was entirely unexpected. The magnetic field just outside the heliopause is roughly aligned with the magnetic field just inside it. Most models before the crossing had predicted a clear change in magnetic field direction at the heliopause, a definitive rotation from the solar Parker spiral orientation to the interstellar field orientation. Voyager 1 found that the field direction changed, but not by much. Voyager 2, approaching from a different direction, confirmed the result. The interstellar magnetic field in the immediate vicinity of the heliopause appears to be running roughly parallel to the solar magnetic field inside it. This alignment was not predicted, and it has significant implications for how the heliosphere interacts with the interstellar medium, suggesting that the interstellar magnetic field is helping to shape the heliosphere's form, and that the two magnetic domains are more coupled than simple models assumed. NASA described the finding in this way. An observation by Voyager 2's magnetic field instrument confirms a surprising result from Voyager 1. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. With Voyager 1, scientists had only one sample and could not say whether the apparent alignment was characteristic of the entire exterior region or just a coincidence. Voyager 2's observations confirm the Voyager 1 finding and indicate that the two fields align. This confirmed alignment is one of several ways in which the Voyager data has pushed heliospheric science into genuinely new territory, revising models that have been built on indirect evidence, providing direct constraints that no remote observation could have supplied, and generating questions that will take decades of additional research to answer. And most people have never heard of it. Section 3. The Crossing. August 25th, 2012. The summer of 2012 was when the instruments aboard Voyager 1 began registering the final transition. The spacecraft was travelling outward at approximately 17 kilometers per second, which sounds fast but covers less than 1.5 million kilometers per day, a distance that barely moves the needle against interstellar scales. It had been travelling for 35 years, and it was approximately 120 astronomical units from the Sun, and the data coming back was changing in a way that the science team had been anticipating for years, watching the numbers shift month by month, building toward a crossing that everyone knew was coming but that no one had ever been able to precisely time. Two instruments in particular told most of the story. The Cosmic Ray Subsystem, which measures high-energy charged particles, and the Low-Energy Charged Particle Instrument, which covers a broader range including lower-energy ions and electrons. Together, these two detectors had been functioning as a particle census for 3.5 decades, counting what was around the spacecraft and where those particles came from. Inside the heliosphere, a substantial portion of the particle environment was composed of anomalous cosmic rays. These are atoms that originated in the interstellar medium as neutral particles, drifted into the heliosphere unimpeded because neutral atoms are not deflected by magnetic fields, became ionized by solar ultraviolet radiation, were picked up by the solar wind, and were then accelerated to high energies at the termination shock. They are interstellar in origin, but solar in their acceleration mechanism. They exist only inside the heliosphere because they require the termination shock to reach their measured energies. In May of 2012, at approximately 120 astronomical units, Voyager 1 detected a rapid increase in galactic cosmic rays. In the same period, the anomalous cosmic ray population began a significant decline, and the crossover was stark and directional. The solar-produced particle population was diminishing. The galactic population was surging. In just 1 month, galactic cosmic rays rose by 9%. Over the preceding 3 years, they had increased by 25%. Then at the end of August 2012, the transition accelerated dramatically. Within a matter of days, the anomalous cosmic ray population dropped to near zero. Not gradually, not over weeks or months, within days. Simultaneously, the count of galactic cosmic rays surged to levels the spacecraft had never recorded during its entire 35-year journey through the heliosphere. The Sun's contribution to the local particle environment dropped to essentially zero. The galactic contribution arrived in full, but the magnetic field data complicated the picture. Scientists had expected that crossing the heliopause would produce a sharp rotation in the magnetic field direction, a clean switch from the solar field orientation, shaped by the Parker spiral and the Sun's rotation, to the interstellar field orientation, which runs at a different angle relative to the solar equatorial plane. Instead, the field direction changed gradually over days to weeks. Some researchers argued this meant Voyager had entered a new unexpected transition region, not quite inside the heliosphere, but not yet fully in interstellar space. Others argued the spacecraft had crossed the heliopause, but that the boundary was more complex than simple models had predicted. The debate played out in journals and at conferences through the second half of 2012 and into 2013, and it would not be resolved by the particle data or the magnetic field data alone. Resolution came from an unexpected source: plasma oscillations. In March of 2012, several weeks before the particle data began its dramatic shift, a powerful coronal mass ejection erupted from the Sun. These events are massive bursts of solar plasma and magnetic field that race outward through the heliosphere at speeds exceeding 1,000 kilometers per second, significantly faster than the normal solar wind. This particular eruption sent a shockwave propagating outward through the solar system. That shockwave travelled for 13 months. On April 9th, 2013, the shockwave from the March 2012 coronal mass ejection arrived at Voyager 1's location, more than 120 astronomical units from the Sun. When the shockwave arrived, it caused the plasma surrounding the spacecraft to vibrate at specific frequencies. Voyager 1's plasma wave science instrument, one of the few still receiving enough power to operate, detected these oscillations clearly. The frequency of plasma oscillations depends directly on the density of the surrounding material. Higher density plasma oscillates at higher frequencies. The oscillations Voyager recorded corresponded to an electron density of approximately 0.08 electrons per cubic centimeter. That was roughly 40 times denser than the plasma density in the outer heliosheath that Voyager had measured before the transition. The measurement was decisive. Working backward through the particle data, the magnetic field records and the plasma wave measurements, the science team pinpointed the crossing. If Voyager 1 had passed through the heliopause on or around August 25, 2012, at a distance of approximately 121.7 astronomical units from the Sun, NASA made the official announcement in September of 2013, more than a year after the actual crossing. For those 13 months, Voyager 1 had been in interstellar space, and no one on Earth had been certain. Don Gurnett at the University of Iowa, principal investigator for the plasma wave science instrument, described the moment his team recognized the oscillations. They literally jumped out of their seats, he said, because the data showed the spacecraft was in an entirely new region, comparable to what was expected in interstellar space, and totally different from anything inside the solar bubble. Ed Stone of the California Institute of Technology, the Voyager project scientist who had been with the mission since before launch, put it plainly. The Voyager team needed time to analyze those observations and make sense of them, but the answer to the question everyone had been asking, "Are we there yet?" was now yes. The plasma wave data also produced something that no one had quite anticipated. When NASA released an audio rendering of the oscillations in September of 2013, converting the plasma wave frequencies into the range of human hearing as a tool for comprehension, what emerged was a thin, sustained tone, almost like a note held on a glass harmonica. It rose and fell slightly as the plasma density fluctuated around the spacecraft. Thin, quiet, continuous. It was not literally sound. The interstellar medium is far too thin to support acoustic vibrations, and what Voyager detected were oscillations in the electric field of the surrounding plasma. Electromagnetic phenomena translated into audio as a way for human minds to perceive the data directly. But the physics underneath was genuine. The interstellar medium vibrates at a characteristic frequency determined by its electron density. That vibration persisted. It did not stop. It continued as a baseline signal rising slightly when a solar-driven disturbance reached Voyager's location and causing the surrounding plasma to oscillate more intensely, then settling back to its quiet hum when the disturbance passed. The interstellar medium has a voice. It is thin and faint and permanent, and Voyager was the first human instrument to hear it. 6 years later, the Voyager 2 crossed the heliopause and provided something Voyager 1 could never have offered: direct plasma measurements. Voyager 1's plasma science instrument, the device designed to directly measure the speed, density, temperature and flow direction of charged particles in the surrounding medium, had failed in 1980, 32 years before the heliopause crossing. Everything Voyager 1 knew about the plasma around it had to be inferred indirectly from those plasma wave oscillations. The calculation was sound, but it was indirect. The instrument was not measuring the plasma. It was measuring the plasma's vibration and working backward to the density. Voyager 2 still had a functioning plasma science instrument. On November 5, 2018, at a distance of approximately 119 astronomical units, the Voyager 2 crossed the heliopause. Its plasma science instrument registered the crossing with unambiguous directness. One moment, the instrument was measuring outward flowing solar wind plasma, decelerated but still clearly moving in a direction away from the Sun, with a speed of roughly 100 to 150 kilometers per second, and a density characteristic of the outer heliosheath. Then that flow ceased entirely. The outward speed of the solar wind dropped to zero. In its place, the instrument detected a plasma population that was denser, hotter in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. This was interstellar plasma, material of galactic origin, never before measured in place by any instrument from Earth. In the density measured by Voyager 2's plasma instrument in the interstellar medium was approximately 0.05 to 0.06 electrons per cubic centimetre. This represented an increase of roughly 20 to 40 times over the solar wind density in the outer heliosheath. Context matters here. By any terrestrial standard, this is still extraordinarily thin. Earth's atmosphere at sea level contains approximately 25 quintillion particles per cubic centimetre. Even laboratory vacuum chambers contain trillions of particles per cubic centimetre. The interstellar medium, at 0.05 particles per cubic centimetre, is, by human experience, indistinguishable from perfect emptiness, but it is not emptiness. And the difference between the heliosheath's thousandth of a particle per cubic centimetre and the interstellar medium's 50th of a particle per cubic centimetre is physically significant. Denser plasma transmits electromagnetic disturbances differently. It supports different wave modes. It exerts more pressure. The density jump at the boundary is the physical manifestation of the confinement that creates the heliosphere in the first place. The temperature of the interstellar plasma, measured by Voyager 2's instrument, was approximately 30,000 to 50,000 Kelvin. This requires careful interpretation. Temperature in plasma physics refers to the average kinetic energy of the particles, not the thermal sensation that a human body would experience. You could immerse your hand in plasma at 50,000 Kelvin in the interstellar medium and feel absolutely nothing, because so few particles would actually strike your skin per second that the total energy transfer would be negligible. Temperature without density produces no perceptible heat, but the temperature is physically meaningful. Plasma at 50,000 Kelvin has been heated by something. Shock waves from ancient supernova, turbulent dissipation of magnetic energy. The general thermodynamic history of the local interstellar medium accumulated over millions of years, and critically, the plasma Voyager 2 measured was essentially stationary. Inside the heliosphere, everything moves outward because the solar wind imposes a radial flow. Outside, the plasma appeared nearly stationary in the spacecraft's reference frame, and this was the interstellar medium at rest, material that is not being blown outward by any local star, but is instead drifting slowly through the galaxy as part of the local interstellar cloud that the solar system is currently traversing. 2 crossings, 2 independent sets of measurements, 2 different locations on the heliopause's surface, sampled 6 years apart, with the Sun at different phases of its activity cycle between them. Together, they built a picture that neither spacecraft could have produced alone. The crossing distances were nearly identical. Voyager 1 crossed at 121.7 astronomical units. Voyager 2 crossed at 119. Given that Voyager 1 crossed during a period of lower solar wind pressure, and Voyager 2 crossed during a different phase of the solar cycle, the similar crossing distances suggested that the heliopause is more structurally stable than some models had anticipated, possibly because the interstellar magnetic field outside the boundary is stronger than earlier estimates had suggested. But the 2 crossings also revealed differences. The plasma conditions at the 2 crossing points were not identical. Voyager 2's direct measurements showed a slightly different density and temperature profile compared to what Voyager 1's indirect plasma wave measurements had indicated at a different location 6 years earlier. The magnetic transition was somewhat sharper at Voyager 2's crossing point than at Voyager 1's, suggesting that the boundary's character varies along its surface. Some sections of the heliopause may be thinner and more abrupt, others may be thicker and more gradual, each with more extensive mixing between solar and interstellar material in the transition layer. These differences are not surprising. The heliopause is not a rigid structure. It is a dynamic boundary between 2 fluid systems shaped by turbulence on both sides, buffeted by coronal mass ejections from within and interstellar pressure variations from without. Expecting it to be uniform would be like expecting the surface of an ocean to be perfectly flat. What the 2 Voyager crossings proved between them is that the heliopause is real, is measurable, is physically definable, and marks a genuine transition to an environment that is measurably and fundamentally different from everything within the Sun's domain. The galaxy, as experienced from inside the solar system, ends at the heliopause, and what lies beyond it changes everything. Before moving forward, it is worth dwelling on the individual instruments and what they specifically registered, because the crossing was not a single measurement. It was a convergence of independent lines of evidence from different sensors, each measuring a different physical property of the surrounding medium, all arriving at the same conclusion from different directions. The Cosmic Ray Subsystem, the instrument that was shut off on February 25th, 2025 to conserve power, consists of a suite of 3 telescopes designed to measure the energy and flux of cosmic ray particles, including protons from both the galaxy and the Sun. In the years before the crossing, this instrument had been tracking the slow infiltration of galactic cosmic rays into the outer heliosphere. During solar minimum, and when the heliosphere's magnetic shielding is weaker, more galactic cosmic rays penetrate inward, and the instrument recorded those variations with the 11-year rhythm of the solar cycle. Then, starting in early 2012, the readings began to diverge from that cyclic pattern. The galactic component climbed, while the anomalous cosmic ray component, the particles produced by acceleration at the termination shock inside the heliosphere, dropped. By August of 2012, the anomalous component was essentially absent. The cosmic ray subsystem confirmed. The spacecraft had left the region where the termination and shock could produce those particles. The Low Energy Charge Particle Instrument, which measures ions and electrons at lower energies, told a complementary story. It tracked the solar wind particles and the populations of particles accelerated by various processes within the heliosphere throughout the mission. In the month before the crossing, it detected a dramatic drop in the solar wind's particle density, eventually registering essentially zero outward flowing solar material. The solar component of the particle environment had vanished. The magnetometer, mounted on a long boom extending away from the spacecraft body to minimize interference from the vehicle's own magnetic signature, tracked the magnetic field direction and strength throughout the crossing region. What it found complicated the interpretation for months. The field strength increased slightly across the heliopause, from the roughly 0.2 nanotesla of the outer heliosheath to the approximately 0.4 to 0.5 nanotesla of the interstellar medium. But the direction changed only gradually, over days to weeks, rather than flipping sharply. The expected rotation from solar to interstellar orientation was present, but smoothed. The transition was not a knife edge. It was a finite transition layer where solar and interstellar magnetic fields blended, possibly permitting limited mixing of material between the heliosphere and the interstellar medium through a boundary that behaves more like a permeable membrane than a wall. And the plasma wave science instrument, which detects electromagnetic oscillations in the surrounding plasma, provided the decisive measurement, and its detection of the plasma oscillations triggered by the March 2012 coronal mass ejection shockwave, arriving in April 2013, allowed the direct calculation of the surrounding electron density and the retrospective confirmation of the crossing date. Together, these four instruments, all designed in the 1970s, all operating far beyond their design lifetimes, all running on a power supply that was already less than half of what it had been at launch, produced a coherent and unambiguous portrait of the most significant boundary crossing in the history of human exploration. Ed Stone, who had spent 4 decades as Voyager project scientist, reflected on the significance of the crossing in terms that captured what the mission represented across its career. The Voyager team needed time to analyse those observations and make sense of them, but the answer to the question everyone had been asking is yes. We have crossed into interstellar space. Stamatis Krimigis, principal investigator for Voyager's Low Energy Charge Particle Instrument, offered an analogy. The crossing was like Voyager leaving the hot, million-degree atmosphere of the Sun and entering into a region dominated by the cold, 5,000-degree atmosphere of the galaxy. It is like the first time a satellite went beyond Earth's atmosphere at an altitude of 600 miles. Voyager is now leaving the solar bubble at an altitude of 11.3 billion miles. It is another historic milestone. The analogy is imperfect, as all analogies are, but it captures something real, and the Earth's atmosphere defines a boundary beyond which the Sun's influence on the local environment is no longer dominant, and the broader context of near-Earth space takes over. The heliopause defines an equivalent boundary, at vastly larger scale, beyond which the Sun's influence on the local environment is no longer dominant, and the broader context of the galaxy takes over. One further detail from the Voyager 2 crossing adds depth to the picture. When Voyager 2's plasma science instrument detected the cessation of the solar wind at the heliopause, it did not detect a gradual fade. The solar wind cut off sharply. One set of measurements showed outward flowing solar material. The next set, a short time later, showed dense stationary interstellar plasma. And the transition was abrupt in a way that confirmed the heliopause is a real physical boundary with a definable location, not just a gradual thinning of solar influence that blends imperceptibly into the interstellar medium. The plasma science instrument on Voyager 2, then went on to sample the interstellar medium directly for several years before being shut down in October of 2024 to conserve power. Its orientation relative to the direction of plasma flow in interstellar space, having made it less productive than earlier in its mission. In its final years of operation, it had collected direct measurements of interstellar plasma density, temperature, and flow velocity that Voyager 1 could never have provided, filling in a dimension of the picture that indirect inference alone could not supply. And when the plasma science instrument was turned off in October of 2024, it was the end of direct interstellar plasma measurements by any instrument ever built. Nothing currently in operation or planned for near-term launch will replace it. The galaxy, as experienced from inside this solar system, ends at the heliopause, and what lies beyond it changes everything. What the shield protects, and what happens without it. The particle data Voyager collected on both sides of the heliopause tells a story about protection that most people have never been asked to think about, because the protection was always there, invisible and unannounced, from the first moment life began on Earth. Let's be specific about what galactic cosmic rays actually are, because the word cosmic ray carries a casual familiarity that undersells what these particles represent. They are not electromagnetic radiation. They are not light, or radio waves, or X-rays, or gamma rays. They are physical particles. Protons make up the largest fraction, approximately 87%. Alpha particles, which are helium nuclei, make up about 12%. Heavier ions, including carbon, oxygen, silicon, and iron, make up the remaining 1% or so, but represent some of the most energetically extreme particles in the galactic environment. These particles travel at velocities that approach the speed of light. Some of them are moving at 99.9% of the speed of light. Some are moving faster still, by fractions that push the definition of what velocity can physically mean for matter. So the energy of individual galactic cosmic ray particles spans a range that is genuinely difficult to process. At the low end, cosmic rays carry energies of a few million electron volts, which is comparable to particles produced in medical equipment used for cancer treatment. At the high end, the most energetic cosmic rays ever detected carry energies exceeding 100 billion electron volts, concentrated into a single subatomic particle smaller than an atomic nucleus. A proton at that energy carries the kinetic energy equivalent of a professionally thrown baseball, compressed into a particle with no physical size that a human instrument can resolve. The primary sources of galactic cosmic rays are supernova remnants. When a massive star exhausts its hydrogen and helium fuel and the core collapses, the resulting explosion sends a shock wave expanding outward through the surrounding interstellar medium at thousands of kilometers per second. This shock wave persists for thousands of years as it gradually decelerates, and throughout that period it continuously accelerates, charged particles trapped in the turbulent magnetic fields at the shock front. The process, called diffusive shock acceleration, allows particles to bounce back and forth across the shock boundary, gaining energy with each crossing. Over thousands of years, this mechanism produces a population of particles with energy spanning many orders of magnitude. Other sources contribute as well. Pulsars, the rapidly rotating neutron stars left behind after certain supernovae, either generate intense rotating magnetic fields and can accelerate particles to high energies in their magnetospheres. At the largest scales, supermassive black holes at the centers of active galaxies generate relativistic jets that produce the highest energy cosmic rays observed. Particles so energetic they may originate in other galaxies entirely and have travelled millions of light years before arriving in the Milky Way. The flux of galactic cosmic rays in interstellar space, as now directly confirmed by the Voyager's instruments, is substantial. It represents a continuous rain of high-energy particles arriving from all directions simultaneously. Some of these particles have been travelling through the interstellar medium for millions of years, scattered and redirected by the tangled galactic magnetic field, and their original source long since faded into a cold remnant or dispersed entirely. The heliosphere blocks approximately 75% of this rain from reaching the inner solar system. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is even more pronounced, with the heliosphere reducing the flux by factors of 5 to 10 or more. When Voyager 1 crossed the heliopause, its instruments recorded the galactic cosmic ray intensity climbing to levels roughly 2 to 3 times higher than the maximum values ever observed inside the heliosphere during the deepest solar minimum periods. The lower energy component, the particles most effectively excluded by the heliosphere's magnetic shielding, it appeared in abundances that the spacecraft had never recorded during its entire 35-year journey inward. The increase was not uniform across all energies. Higher energy cosmic rays, those with greater momentum, penetrate the heliosphere more readily, and had been present in partial measure inside the outer heliosheath. They showed a more gradual transition at the boundary. Lower energy particles, the ones most effectively excluded, showed a sharp step function at the heliopause. They were simply absent inside and present in full outside. This distinction matters, because lower energy cosmic rays are also the most biologically damaging per particle relative to the protection typically available, and when a high energy cosmic ray proton strikes a material surface or passes through biological tissue, the interaction is not like absorbing sunlight. The proton does not deposit its energy gradually and then stop. It punches through matter, ionizing atoms along its path, and if it has enough energy it can shatter atomic nuclei, producing a cascade of secondary particles that spread outward from the impact point. Neutrons, additional protons, pions, muons and gamma rays spray through the surrounding material, sometimes depositing more total energy inside a structure than the original cosmic ray would have delivered on its own. This secondary particle production is one of the most counterintuitive facts of high-energy radiation physics. Adding more shielding material above a certain thickness can actually increase the radiation dose received inside, because the shielding generates more secondary particles than it stops. For biological tissue specifically, the concern is not just the total energy deposited, but the spatial pattern of DNA damage. A heavy cosmic ray nucleus, such as an iron ion travelling at nearly the speed of light, can destroy every cell along its track, through tissue in a straight line of concentrated damage. The resulting DNA lesions are qualitatively different from those caused by lower energy radiation. They involve clustered breaks in the DNA double helix that are far more difficult for cellular repair mechanisms to address. The body's DNA repair systems evolved in an environment where single-strand breaks and isolated double-strand breaks are the norm. A dense cluster of simultaneous breaks at the same location is a different problem, one where repair is less reliable and errors are more likely to persist. The biological consequences of this kind of chronic exposure are what concern space agencies most deeply when planning missions beyond Earth's magnetosphere. Astronauts aboard the International Space Station, orbiting within both Earth's magnetosphere and the heliosphere, receive radiation doses that are carefully monitored and limited by mission duration constraints. The exposure is roughly 10 times higher than the surface average, primarily from trapped radiation in the Van Allen belts and from cosmic rays that penetrate both shields. Even this modest exposure motivates the radiation limits that cap astronauts' career doses. A crew travelling beyond the heliopause would face the full unshielded galactic cosmic ray flux that Voyager's instruments measured. radiation dose rates in interstellar space, and extrapolated through standard radiation transport models from Voyager's measured particle fluxes, would substantially exceed annual limits imposed by every major space agency, not just for a brief period during a particularly active event, but continuously for the entire duration of transit. The cumulative dose over a multi-decade interstellar journey would pose risks of elevated cancer rates, cardiovascular damage, cataracts, and effects on the central nervous system, including cognitive changes. These are not speculative. They are direct extrapolations of measured particle fluxes using decades of established radiation biology. Active shielding concepts using powerful superconducting magnets to generate an artificial magnetosphere around a spacecraft have been proposed as potential alternatives to passive mass shielding. The physics is sound. A strong enough magnetic field deflects charged particles before they reach a vehicle's hull, mimicking what the heliosphere and Earth's magnetosphere do naturally. The engineering is staggering, generating a magnetic field capable of deflecting cosmic rays with energies of billions of electron volts requires superconducting coils of enormous mass, carrying currents that would produce intense fields in the living quarters with their own potential biological effects. The power required to sustain such a field continuously for decades exceeds what any existing or foreseeable power system aboard a spacecraft could provide. But the heliosphere's protective role extends beyond shielding biological tissue. It also mediates the radiation environment on planetary surfaces and in planetary atmospheres throughout the solar system. Consider Mars. The planet lost its global magnetic field billions of years ago, and its atmosphere is only about 1% as thick as Earth's, providing minimal shielding. Despite these disadvantages, Mars still benefits from the heliosphere. The cosmic ray flux at the Martian surface is substantially higher than at Earth's surface, because Mars lacks the magnetosphere that provides Earth's second layer of protection, but it is still significantly lower than the full galactic value because the heliosphere continues to reduce the external flux before any of it can reach Mars. Without the heliosphere, the baseline radiation environment at the Martian surface would be considerably more hostile, and the rate of radiolysis of any subsurface water ice would increase. The production of oxidizing compounds in the Martian soil would accelerate. The already challenging prospects for any potential Martian subsurface chemistry would become more difficult. The moons of the outer solar system, including Europa around Jupiter, Enceladus around Saturn, and Titan, also exist within the heliosphere's protection. These moons are among the most compelling candidates in the solar system for environments that might support, or might once have supported, some form of chemistry relevant to life. Their ice shells and the liquid water, oceans hypothesized beneath them, are exposed to cosmic rays, but the heliosphere reduces the external flux before those rays reach the outer solar system. Remove the heliosphere, and the radiation bombardment of their ice surfaces increases. The chemistry in the environments beneath the ice over geological timescales would be altered. Even on Earth, the numbers are instructive. The heliosphere combined with Earth's magnetosphere and atmosphere reduces galactic cosmic ray exposure at the surface by an enormous factor compared to the unshielded interstellar value. At aircraft altitudes, where much of the atmosphere's shielding is gone, radiation from cosmic rays is measurable and is one of the factors that aviation regulatory bodies and airlines consider when calculating occupational exposure limits for flight crew. At the surface of the Moon, which has no atmosphere and relies entirely on the heliosphere as its only shield, the cosmic ray environment is significantly more intense than at Earth's surface, and any long-duration lunar surface operations require radiation protection strategies as a result. the heliosphere is not incidental to the conditions that make the inner solar system a relatively benign environment. It is foundational to them. It represents the outermost layer of a nested protection system that steps down the full galactic cosmic ray flux by roughly 3 orders of magnitude between interstellar space and the surface of the Earth. Take away the heliosphere and the protection provided by the innermost layers, the magnetosphere in the atmosphere is working against a much larger input. Everything alive on Earth exists at the bottom of this protection stack, and none of it is guaranteed. There is a further dimension to what the heliosphere protects that is worth making explicit, because the cosmic ray shielding is only part of the picture. The heliosphere also regulates the flux of interstellar neutral atoms that reach the inner solar system. Neutral hydrogen atoms from the interstellar medium drift into the heliosphere continuously. Because they carry no electric charge, they are not deflected by the heliosphere's magnetic field the way charged cosmic ray particles are. They pass through the heliopause relatively freely and travel inward through the heliosphere, where some become ionized by solar, ultraviolet radiation, or charge exchange with solar wind protons. Once ionized, they are incorporated into the solar wind and eventually accelerated at the termination shock, becoming the anomalous cosmic ray population that Voyager detected and that vanished so decisively upon the heliopause crossing. This process normally keeps the flux of interstellar neutral material reaching the inner solar system quite low, but when the heliosphere is compressed by encounter with a dense interstellar cloud, the neutral atom flux inside the heliosphere increases substantially. A dense cloud like the local Lynx of Coal cloud, with a neutral hydrogen density of approximately 3,000 particles per cubic centimetre, would expose Earth not only to increased cosmic ray flux, but to a direct influx of interstellar neutral hydrogen in quantities orders of magnitude above normal. This influx could alter atmospheric chemistry in ways that differ from the well-studied effects of cosmic ray ionization alone. Researchers at Washburn University published a study in the 2024 in Geophysical Research Letters examining what would happen to Earth's upper atmosphere during the kind of heliospheric compression events modelled by Ofer and colleagues. Their analysis found that Earth's mesosphere, the atmospheric layer roughly 50 to 80 kilometres above the surface, would receive dramatically increased hydrogen inputs during a dense cloud crossing. The influx of hydrogen atoms interacting with atmospheric oxygen would produce elevated concentrations of water vapour at high altitudes, potentially generating global noctilucent cloud formation. Though the study found these clouds would likely remain confined to polar latitudes and seasonal patterns rather than covering the entire sky. And they also found that polar mesospheric ozone would become significantly depleted during such events, though the total ozone column broadly increases due to other chemical pathways. The picture that emerges from combining all of this research is one of the heliosphere as not merely a radiation shield, but as a chemical boundary. Inside the heliosphere, the inner solar system's atmospheric chemistry, its surface water, its magnetic environment, and its cosmic ray flux all operate within parameters set by the solar wind's dominance. Outside those parameters, everything changes. The heliosphere is the sun's way of defining the local conditions that exist within its domain, and those conditions are what made Earth's evolution of complexity possible. This perspective has relevance for thinking about habitability in systems other than our own. Every star on the main sequence produces some form of stellar wind, which inflates some form of astrosphere. Red dwarf stars, which constitute roughly 70% of all stars in the Milky Way, are small, cool, and produce relatively weak winds. Their astrospheres may be significantly smaller than the Sun's heliosphere. For planets in the habitable zones of red dwarfs, which must orbit much closer to their host star than Earth does because red dwarfs are intrinsically much dimmer, the question is, whether those planets sit inside an astrosphere sufficient to reduce galactic cosmic ray flux to levels compatible with complex atmospheric chemistry. Some models suggest that habitable zone planets around red dwarfs remain inside their host star's astrosphere, but the margin may be thin. A period of elevated interstellar medium density saw a reduction in stellar wind output due to the star's own activity cycle, could compress the astrosphere inward and temporarily expose planets in the habitable zone to the full galactic cosmic ray environment. For planets that already lack strong intrinsic magnetic fields, which red dwarf habitable zone planets may not have, because tidal locking to their host star can affect interior dynamics, this would represent a significantly more challenging radiation environment than Earth experiences. The Sun's heliosphere is not typical. It is the heliosphere of a star that happens to be located in a relatively low density region of the interstellar medium, producing a wind output that maintains a large and effective protective bubble. Stars in denser regions of the galaxy, particularly within spiral arms where interstellar medium density is higher and supernova rates are elevated, would have smaller, more compressed astrospheres. Their habitable zone planets, if they exist, would experience higher cosmic ray fluxes and more frequent episodes of heliospheric compression. The heliosphere, in this context, is not just infrastructure for our solar system. It is a variable, a parameter of habitability that differs from star to star and region to region across the galaxy. Understanding it matters not just for understanding Earth's history, but for understanding where in the galaxy the conditions for complex evolution are most reliably maintained. Everything alive on Earth exists at the bottom of this protection stack, and none of it is guaranteed. But the bubble has collapsed before the heliosphere has not always been the size it is today. This is the part that transforms the heliosphere from a reassuring feature of our solar system into something far more fragile and contingent. The heliosphere is not a fixed structure. It is not an immovable shield that the Sun erected once and that has remained unchanged through the 4.5 billion years of Earth's existence. It breathes, it responds to conditions, and those conditions have changed dramatically at multiple points in the geological past. The evidence for that is preserved in the sediment at the bottom of the ocean, in ice cores drilled from Antarctica, and on the surface of the Moon in isotopes that do not belong there. And the size of the heliosphere at any given moment is determined by a balance of pressures. The solar wind pushes outward. The interstellar medium pushes inward. The heliopause sits where those pressures equilibrate. Change either pressure and the heliopause moves. The solar wind pressure can change. It varies with the solar cycle on timescales of 11 years. It varies with the Sun's overall activity level on longer timescales. As the Sun ages and evolves, its wind properties will change on billion-year timescales. But the solar wind has been relatively stable throughout the period of complex life on Earth. The interstellar medium pressure is a different story. The solar system is not sitting still. It is orbiting the centre of the Milky Way at approximately 230 kilometers per second, completing one orbit roughly every 230 million years. As it orbits, it moves through different regions of the galaxy, encountering different conditions in the interstellar medium. Some regions are relatively empty, with low particle densities and modest pressures. Other regions, particularly inside the spiral arms where star formation is actively occurring, are denser, more turbulent, and exert significantly greater inward pressure on the heliosphere. Right now, the solar system is passing through a region called the local interstellar cloud, a warm, partially ionized patch of gas roughly 30 light years across. The current density of this cloud outside the heliopause is approximately 0.1 to 0.3 particles per cubic centimetre, and its temperature is roughly 6,000 to 8,000 Kelvin. And these are the specific conditions that Voyager 1 and Voyager 2 measured just beyond the heliopause. They are the conditions that currently determine how far the heliosphere extends, roughly 120 astronomical units in the upstream direction. The solar system is near the edge of this cloud. Depending on the models used to trace the solar system's trajectory and the cloud's own motion, we will likely exit into a different region of the interstellar medium within the next few thousand to tens of thousands of years. What that region is like will determine whether the heliosphere grows or shrinks. And there is geological evidence that this kind of change has happened before, with consequences that reached all the way to the surface of Earth. Studies of deep-sea sediments, Antarctic ice cores, and lunar surface samples have detected anomalous concentrations of iron-60 and plutonium-244. These are radioactive isotopes produced in supernova explosions, not in any terrestrial geological process. Iron-60 has a half-life of approximately 2.6 million years. Plutonium-244 has a half-life of about 80 million years. Finding elevated concentrations of either isotope in materials deposited at specific points in Earth's geological record is a direct signature of interstellar material reaching Earth, material that would normally be filtered out by the heliosphere. Elevated iron-60 and plutonium-244 levels have been found in sediment layers corresponding to periods roughly 2 to 3 million years ago, and again, around 7 to 8 million years ago. These deposits suggest that during those epochs, something changed. Either a nearby supernova sent a wave of isotope-enriched material through the local interstellar medium, or the heliosphere was compressed enough to allow interstellar material to reach Earth directly, or both. In June of 2024, a team led by astrophysicist Merav Ofer of Boston University, working from research she began during a fellowship at Harvard's Radcliffe Institute, published a study in the journal Nature Astronomy that provided the most detailed quantitative model yet of what may have happened during the period corresponding to approximately 2 to 3 million years ago. The paper identifies a specific structure in the local interstellar medium called the local links of cold cloud, which is part of a larger string of dense hydrogen clouds called the local ribbon of cold cloud system. Using sophisticated computer models to trace the solar system's path backward through space and simultaneously tracking the motion of these cloud systems, Ofer and her collaborators found that the solar system's trajectory may have intersected the local links of cold cloud between 2 and 3 million years ago. The local links of cold cloud is not like the current environment outside the heliopause. It is a cold, dense cloud composed primarily of hydrogen atoms. Its particle density is estimated at approximately 3,000 particles per cubic centimetre. The current interstellar medium outside the heliopause has a density of about 0.1 particles per cubic centimetre. The local links of cold cloud is 30,000 times denser. The simulation showed what would happen to the heliosphere under those conditions. And the heliopause would be compressed inward by the enormous increase in external pressure, not to 100 astronomical units, not to 50. The model found that during the passage through this dense cloud, the heliosphere would shrink to a scale of approximately 0.22 astronomical units, smaller than Earth's orbit around the Sun. That would have placed the Earth outside the heliosphere entirely, for a period ranging from a few hundred years to potentially 1 million years, depending on the size of the cloud and the precise geometry of the encounter. The Earth and all the inner planets would have been in direct contact with the dense interstellar medium. The heliosphere, the protective bubble that had enveloped Earth for the previous 4 billion years, would have been compressed into a tiny shell surrounding only the innermost fraction of the solar system. Earth would have been exposed to the full, unmoderated interstellar medium of a dense molecular cloud with a neutral hydrogen density above 3,000 particles per cubic centimetre and a galactic cosmic ray flux increased by roughly an order of magnitude or more compared to what Earth experiences today. The paper argues that this scenario is consistent with the geological evidence. The elevated iron-60 and plutonium-244 found in ocean sediments, Antarctic ice, and lunar samples from approximately 2 to 3 million years ago would be explained by the direct delivery of interstellar material to Earth during a period when the heliosphere was no longer intercepting it. And the timing also correlates with geological temperature records indicating the onset of a significant cooling period on Earth around the same epoch, the beginning of the Pleistocene glaciations, the cycle of ice ages that continued until approximately 12,000 years ago. Whether the interstellar cloud encounter directly caused or contributed to those ice ages remains an open scientific question. The physical mechanisms connecting increased cosmic ray flux to climate change are real. Cosmic rays can ionize the lower atmosphere and influence cloud nucleation, affecting cloud cover and planetary albedo. Incoming interstellar hydrogen can alter atmospheric chemistry. These are effects that climate models can evaluate. Whether the magnitude was sufficient to trigger or sustain the Pleistocene glaciation cycle is something that researchers, including Ofer and her collaborators at BU's Shield Center, are continuing to investigate. What is not in question is the physical mechanism. The heliosphere can be compressed. The geological record contains evidence that it was compressed to the point of exposing Earth to the interstellar medium, and our early human ancestors, Homo habilis and early Homo erectus, were alive during the period when this may have occurred. They were walking on a planet that was, for some period of time, unshielded. They had no awareness of it, no ability to measure it or respond to it, no way to know that the invisible structure that had protected their planet since long before their species existed had, temporarily, collapsed around them. Harvard professor Avi Loeb, who collaborated on the study, put it simply: only rarely does our cosmic neighbourhood beyond the solar system affect life on Earth. It is exciting, he said, to discover that our passage through dense clouds a few million years ago could have exposed Earth to a much larger flux of cosmic rays and hydrogen atoms. Merov Ofer, reflecting on the broader implication of the work, described it this way: stars move, and now this paper is showing not only that they move, but they encounter drastic changes. The heliosphere is not a fortress, it is a tent erected by the solar wind, held up by the continuous outpouring of charged particles from the corona, pressed upon from all sides by an interstellar medium whose properties change as the solar system moves through the galaxy, and the tent holds today. It has held for most of Earth's history, with only occasional interruptions, but it is shaped by its environment, and that environment is not static. When the solar system next encounters a dense interstellar cloud, the tent will compress again. The timing and magnitude are uncertain. The trajectory of the solar system through the galaxy is mapped by missions like the European Space Agency's Gaia spacecraft, which is building the largest three-dimensional star map in history, and researchers are using that data to trace the solar system's path both backward and forward in time. Ofer's team is working to extend the modelling back 7 million years, using Gaia data to track where the solar system was and what interstellar structures it may have encountered along the way. The future is harder to model precisely, and because predicting the detailed distribution of interstellar clouds along a trajectory that extends millions of years forward requires information about how those clouds evolve and move over time. What can be said is this: the encounter 2 to 3 million years ago was not the first, and it will not be the last. The solar system's orbit around the galactic centre has taken it through regions of varying interstellar medium density for 4.5 billion years. Each passage through a spiral arm increases the probability of dense cloud encounters. Each entry into a quieter inter-arm region allows the heliosphere to expand. The bubble breathes, it always has. The difference now is that we know it, because a machine the size of a small car told us exactly what waits on the other side when it stops breathing. The implications of the 2024 Nature Astronomy study extend further than the 2 to 3 million year event it modelled. The research opened a new framework for thinking about Earth's long-term climate and biological history that had not previously been systematically explored. Before OFA's work, geologists and climate scientists modelling ice ages over the past few million years focused primarily on factors intrinsic to the Earth-Sun system, the Milankovitch cycles, which describe periodic variations in Earth's orbital shape, axial tilt and precession with periods of roughly 20,000, 40,000 and 100,000 years, plate tectonics and the resulting changes in ocean circulation and atmospheric carbon dioxide, volcanic activity and its effects on greenhouse gases, and the distribution of continents that affects where ice can accumulate and persist. These intrinsic factors are real and important. They cannot be separated from the climate record. But OFA's paper suggests that at least one of the major climate transitions in Earth's recent geological history, the onset of the Pleistocene glaciations around 2 to 3 million years ago, may have had a contribution from an external galactic factor that has not previously been included in climate models: the compression of the heliosphere by a dense interstellar cloud. The geological evidence for the event is not based solely on the Iron-60 and Plutonium-244 isotope anomalies. There is also a broader pattern of increased interstellar dust deposition recorded in ocean sediments from that period, and consistent with a time when the heliosphere was reduced in effectiveness and interstellar material could penetrate more deeply into the inner solar system. Interstellar dust grains normally are modulated by the heliosphere, much as charged particles are, but through different mechanisms, and an increase in dust deposition at Earth's surface during a period of heliospheric compression is consistent with the model. OFA has been explicit about the current limitations of the work. The cloud encounter is inferred from models of the solar system's past trajectory and the position of interstellar cloud structures, not from a direct real-time measurement of what the solar system was doing 2 million years ago. The models depend on assumptions about how the clouds have moved and evolved over that period, and those assumptions introduce uncertainties. The correlation between the geological record and the model's predicted timeline is suggestive, but not yet proof of causation. The BU Shield Center is continuing to refine the models and to investigate what specific atmospheric and surface effects might have followed from the kind of heliospheric compression the study found. The follow-on Geophysical Research Letter study, published later in 2024 and examining the atmospheric effects directly, found that the mesospheric responses to dense cloud crossing events would be measurable in geological records if the right proxy records are available. This opens the possibility that future studies of ice cores, deep-sea sediments, and other paleoclimate archives might be able to identify specific atmospheric chemistry signatures consistent with a period of heliospheric compression, providing an independent line of evidence beyond the isotope anomalies. Avi Loeb, who collaborated on the Nature Astronomy paper, described the research in terms that placed it in its appropriate scientific context. He noted that, while it is rare for our cosmic neighbourhood to affect life on Earth, the passage through dense clouds a few million years ago could have exposed Earth to a much larger flux of cosmic rays and hydrogen atoms, and that the results open a new window into the relationship between the evolution of life on Earth and our cosmic neighbourhood. That last phrase is worth lingering on. The relationship between the evolution of life on Earth and our cosmic neighbourhood. And the neighbourhood, in this context, is not just the other planets and the Sun. It is the local interstellar medium. It is the density and temperature and composition of the gas and dust that the solar system moves through as it orbits the galactic centre. It is the proximity of recent supernovae. It is the structure of nearby molecular clouds. All of these things affect the heliosphere's size, and the heliosphere's size affects the conditions on Earth's surface, and the conditions on Earth's surface affect what kinds of organisms can evolve, survive, and develop over geological timescales. Life on Earth is not just a product of Earth's internal geology and the Sun's radiation output. It is a product of the solar system's specific location in the galaxy, at this specific time, moving through this specific region of the interstellar medium. And the heliosphere is the interface between those scales. It is where the Sun's local influence meets the galaxy's larger context. And it is not a passive boundary. It is an active mediator, shaped by both sides simultaneously, translating galactic conditions into local ones and local ones into the protection that everything inside it enjoys. The difference now is that we know it, because a machine the size of a small car told us exactly what waits on the other side when it stops breathing. The ocean between the stars. It is worth pausing here and being precise about what the interstellar medium actually is, because the word emptiness gets used as a synonym for the space between stars, and Voyager's data shows that this is wrong in a way that matters. And the interstellar medium is not empty. It has density, temperature, magnetic structure, and a radiation environment that does not originate from any nearby star. It presses inward against the heliosphere from every direction. It carries the chemical fingerprints of supernovae that exploded millions of years before our solar system formed. It contains particles that have been bouncing through the Milky Way for longer than the Sun has existed. It hums at a frequency determined by its electron density, a thin, persistent electromagnetic voice that Voyager's instruments detected and recorded the moment the spacecraft crossed into it. But it is also extraordinarily thin. To put the density in perspective, a cubic volume of interstellar medium the size of the Earth would contain only a few thousand tons of material, roughly the mass of a single large ocean-going cargo ship. Individual atoms in the interstellar medium may be separated from their nearest neighbours by distances measured in centimetres or metres. The medium is transparent to visible light. You could see through it for light years without encountering the faintest optical haze. A human hand passed through it would feel nothing, touch nothing, register nothing. The collision rate between a biological object and the neutral atoms of the interstellar medium is negligibly small, and yet the medium is not inert, it is magnetically structured. The galactic magnetic field that runs through the local interstellar medium is approximately 0.3 to 0.5 nanotesla in strength, slightly stronger than the exhausted solar magnetic field in the outer heliosheath at the heliopause. It runs at an orientation significantly different from the Sun's own field. The interstellar magnetic field is woven through the medium on scales ranging from the size of the solar system to thousands of light years, shaped by the accumulated effect of supernova shock waves, the relative motion of interstellar clouds, and magnetohydrodynamic instabilities inherent to any electrically conducting fluid threaded by magnetic fields over geological time. It is mildly turbulent. Voyager's magnetometer recorded fluctuations in both field strength and direction on timescales of hours to days after the heliopause crossing. These fluctuations reflect the ongoing dynamical evolution of the interstellar plasma, driven by processes operating on spatial scales far larger than the spacecraft could sample directly. The medium is not at rest. It is not in equilibrium. It is continuously stirred by forces that have nothing to do with our Sun and that operate on the scale of the galaxy itself. And it is bathed in a radiation field of its own. The galactic cosmic ray flux that Voyager measured in interstellar space arrives from all directions simultaneously, an isotropic rain that does not let up. It is the cumulative product of every supernova that has exploded in the Milky Way over billions of years, every pulsar that has spun down and continued radiating, every binary system that has generated particle acceleration through interaction. The radiation field in the local interstellar mediums is a palimpsest, an accumulated record of the galaxy's violence written in the particle energies. This is the medium that fills the space between every star, and not just the space between our Sun and the nearest star, all of it, the space between every pair of stars in the entire galaxy. And the scale of that space is something human intuition is not equipped to process intuitively, which is why the numbers matter. The nearest star system to our own is Alpha Centauri, approximately 4.3 light years away. 1 light year is the distance that light, travelling at 300,000 kilometers per second, covers in a full year. It is approximately 9.5 trillion kilometers. Alpha Centauri is 4.3 times that distance away, more than 40 trillion kilometers. Voyager 1 is currently travelling at approximately 17 kilometers per second. At that speed, it would take Voyager roughly 73,000 years to reach Alpha Centauri if it were heading in that direction, which it is not. It is heading toward a different part of the sky, and will pass within about 1.6 light years of the star Gliese, 445 in approximately 40,000 years. Even at 10% of the speed of light, a velocity approximately 2,000 times faster than Voyager, and far beyond any propulsion technology that currently exists for any macroscopic spacecraft, the journey to Alpha Centauri would take approximately 43 years. During every one of those 43 years, any spacecraft and any crew aboard it would be immersed in the environment Voyager measured. Full galactic cosmic ray flux, no solar power, temperatures drifting toward 2.7 Kelvin, the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang. No heliosphere, no magnetosphere, no secondary atmosphere, nothing between the crew and the full, unmoderated radiation field of the galaxy. The radiation problem is not merely a matter of adding more shielding. At galactic cosmic ray energies, passive shielding has hard physical limits. Adding aluminum or steel beyond a certain thickness generates more secondary particles through spallation than it stops. The cascade of secondary particles from a high-energy proton or ion nucleus punching through thick shielding can actually increase the total dose to anything on the inside, compared to thinner shielding or no shielding at all. Engineers have explored hydrogen-rich materials, particularly polyethylene and water, use more effective passive shielding because hydrogen's single proton nucleus transfers momentum more efficiently to incoming cosmic ray protons without generating heavy secondary fragments. Studies estimate that optimized polyethylene shielding can reduce galactic cosmic ray dose rates by roughly 30 to 50%. This is meaningful, but the reduction still leaves a crew exposed to doses that would far exceed career limits over a multi-decade transit. Active magnetic shielding, an artificial magnetosphere around the spacecraft, addresses the problem from first principles but requires superconducting, coils large enough and current strong enough to deflect particles with momenta corresponding to billions of electron volts per nucleon, and the mass and power requirements for such a system using any technology currently available or under realistic near-term development, would be an extraordinary fraction of any spacecraft's total mass budget. The coils would need to be sustained continuously, without interruption or degradation, for decades. The energy problem is separate but equally fundamental. Inside the heliosphere, spacecraft can use solar panels for power out to roughly 5 astronomical units. Beyond that, the solar flux falls off with the square of distance and becomes impractically weak. The Voyagers use radioisotope thermoelectric generators, converting the heat from decaying plutonium-238 into electricity. Plutonium-238 has a half-life of 87.7 years. After one half-life, power output is halved. After 2 half-lives, it is reduced to a quarter. A journey of even 50 years would see the power drop to roughly 75% of the initial value, still manageable for an automated probe. But a journey of thousands of years, which is the minimum timescale for any interstellar transit at speeds achievable with near-term technology, would exhaust any radioactive fuel source within a tiny fraction of the total journey time. The interstellar medium itself offers no energy. There is no sunlight to collect. The particle density is far too low to fuel any ram, scoop or drag-based collection system at the speeds a spacecraft would be travelling. The thermal energy of the plasma is thermodynamically inaccessible. An interstellar spacecraft would carry every joule of energy it would ever use from the moment of departure. No resupply, no refueling, no external source. That temperature is a third fundamental challenge. Far from any star, an unheated object in the interstellar medium radiates its thermal energy into the cosmic microwave background and approaches thermal equilibrium at 2.7 Kelvin. At that temperature, lubricants used in mechanical systems solidify, battery electrolytes freeze, structural metals used in spacecraft construction become brittle in ways that Earth-based testing cannot fully replicate. Electronic components designed for the temperature ranges encountered anywhere in our solar system would require continuous active heating, which requires continuous power, which returns to the energy problem. Every major technical challenge of interstellar travel compounds the others. More shielding means more mass. More mass requires more propulsion energy to accelerate. More power for active shielding and active heating means more generator mass or more exotic fuel. The engineering is not simply hard. It is a web of interdependencies where solving one problem with brute force makes the others worse. This is not a reason for despair. It is a description of reality. And the reality, as Voyager's measurements have now confirmed directly, is that the space between stars is not a passive corridor waiting to be travelled. It is an active, irradiated, thermally hostile environment that must be endured for the full duration of any transit. The distance is formidable, but the medium filling that distance is the more fundamental obstacle. There is a broader perspective here that the Voyager data makes unavoidable. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each star that produces a stellar wind, which includes most main sequence stars, inflates its own protective bubble analogous to our heliosphere. These astrospheres vary enormously. Massive hot stars with powerful winds create large astrospheres extending hundreds of astronomical units. Small red dwarf stars with weak winds create astrospheres that may barely encompass their habitable zones. But regardless of the size of any individual astrosphere, the space between those bubbles is the interstellar medium, and Voyager has told us exactly what that medium contains. Galactic cosmic rays, magnetic turbulence, cold plasma, emptiness punctuated by radiation. Every star system in the galaxy is an island. Surrounded by this ocean, the astrospheres are harbours, the interstellar medium is the open water, and the open water is hostile. Yet the volume of the galaxy occupied by astrospheres is vanishingly small compared to the total galactic volume. If every stellar wind bubble around every star in the Milky Way could be added together, the combined protected volume would represent a tiny fraction of the galaxy's total volume. The overwhelming majority of the Milky Way, by volume, is interstellar medium, thin gas, magnetic fields, cosmic rays, cold. The vast dark majority of the galaxy is the ocean, not the islands. This inverts the popular image of the Milky Way. When people picture our galaxy, they tend to imagine a luminous spiral dense with stars, a cosmic city with countless potential destinations connected by paths that could in principle be travelled. The reality is closer to a vast, dark, irradiated wilderness with tiny protected oases scattered impossibly far apart. And the oases are real. The stars burn, but the wilderness between them is the dominant feature, measured by volume, by mass, by the fraction of the galaxy's extent that is inhospitable to anything that evolved inside a protective stellar bubble. Any civilization that might exist anywhere in this galaxy faces the same barrier. They live inside their own stellar bubble, shielded from the galactic environment by their own star's wind, by their own planet's magnetic field, by their own atmosphere. If they look outward and think about reaching the next star, they confront the same interstellar medium that Voyager measured, the same cosmic ray flux, the same absence of energy sources, the same thermal hostility, the same radiation-saturated void stretching light years in every direction. And the physics does not change depending on who you are or what star you orbit. This observation connects directly to one of the most famous unresolved questions in science, the one that physicist Enrico Fermi posed at lunch in Los Alamos in 1950 when he asked, essentially, if the galaxy is full of stars and potentially habitable worlds, where is everyone? Why, in a universe 13.5 billion years old with hundreds of billions of potentially habitable planets, has no clear evidence of any other technological civilization ever reached Earth? Voyager's data does not answer that question, but it illuminates one component of it with new precision. The interstellar medium is not a highway connecting civilizations, it is a barrier separating them, and the space between astrospheres is not neutral territory that any sufficiently advanced technology can simply cross. It is a continuously hostile environment that imposes specific physical requirements: radiation protection, energy density, thermal management that scale with the duration of transit and that become more demanding the longer the journey. Light and radio waves cross the interstellar medium easily. Electromagnetic signals propagate through the thin plasma, attenuated by distance and slightly dispersed by the free electrons in the medium, but fundamentally capable of bridging the gaps between stars. The round-trip signal delay to the nearest star exceeds 8 years, and any exchange of information with a civilization at galactic distances would take longer than human civilization has existed to complete. But the signals travel. Sending matter, a probe, a ship, a person, requires surviving the medium rather than merely passing a signal through it. The galaxy may be a place where information can travel between star systems, but where matter effectively cannot, or cannot without extraordinary difficulty, far beyond anything our current technology can approach. Civilizations might detect each other's electromagnetic signals across hundreds or thousands of light years while remaining permanently isolated by the medium that separates every star from its neighbours. The galaxy could be full of voices and empty of visitors, full of knowledge and devoid of contact. Every civilization and island, able to see the distant light of other fires across the water, and but unable to reach them through the hostile ocean that separates every star from every other star. It is worth being precise about what achieving even modest interstellar transit velocities would require, because the numbers bring the challenge into focus in a way that broad descriptions cannot. Voyager 1's current speed of approximately 17 kilometers per second is the result of a gravitational assist from Saturn. No engine aboard the spacecraft is producing thrust. This speed is free, in a sense, gained by borrowing momentum from a giant planet, but it is also fixed. Voyager cannot go faster. It has no fuel for additional acceleration. The spacecraft will not reach the nearest star system in any time frame relevant to human civilization, or to any civilization with a history comparable to ours. At reaching 10% of the speed of light, with a spacecraft of even modest mass requires an energy input that dwarfs anything human civilization currently produces. At 10% of light speed, roughly 30,000 kilometers per second, a spacecraft with a mass of 1,000 kilograms, which is approximately Voyager's mass, would have a kinetic energy of roughly 4.5 times 10 to the 17th joules. That is more than the total energy output of the entire global human economy for approximately 3 months. To accelerate a crewed spacecraft, which would need to be orders of magnitude more massive than Voyager to support life support systems, radiation shielding, food, water, and the infrastructure of a multi-decade journey, would require energies measured in fractions of the Sun's total annual output. The propulsion concepts that have been seriously analysed for interstellar travel in the physics and engineering literature: nuclear pulse propulsion using detonations to generate thrust, antimatter annihilation drives, laser-driven light sails pushing gram-scale probes rather than crewed vehicles, all face either engineering challenges that are staggering with current technology, or fundamental physics limits that constrain what can be achieved even in principle. None has progressed beyond preliminary theoretical analysis and laboratory-scale demonstrations. This does not mean interstellar travel is impossible in principle. Physics does not forbid it, but it situates the challenge in its correct context. The interstellar medium is not the only barrier to reaching the nearest star. It is one of several barriers, each requiring solutions of comparable difficulty, and the solutions to those other barriers would then place any crew or probe directly into the medium that Voyager measured. The ocean is wide, the physics of crossing it is hard, and the ocean itself is hostile to anything that tries. The silence at the end of the signal. Voyager 1 and Voyager 2 will go silent. Not in a dramatic final transmission, not with a last recorded message or a deliberate farewell. The power will simply continue its slow decline, 4 watts per year lost to the decay of plutonium-238, and at some point the remaining electricity will no longer be sufficient to power the transmitters that have been sending data back to Earth for nearly half a century. And that moment is closer than most people realise. As of February 25th, 2025, NASA turned off the cosmic ray subsystem aboard Voyager 1 to conserve power. 3 science instruments remain operational: the magnetometer, the plasma wave science instrument, and the low energy charged particle experiment. Mission engineers at JPL have implemented a careful power conservation plan, and with those measures in place, they believe the 2 probes could continue operating at least 1 science instrument each into the 2030s. But they are also mindful, as a JPL statement put it, that the Voyagers have been weathering deep space for 47 years, and that unforeseen challenges could shorten that timeline. There have already been scares. In October of 2024, Heine Power Management Command sent to Voyager 1 to activate a heater triggered the spacecraft's fault protection system, which responded by switching from the primary X-band radio transmitter to a much weaker S-band transmitter that had not been used since 1981. For nearly a month, engineers could not receive reliable science data from the spacecraft while they searched for and locked onto the faint S-band signal. They eventually commanded Voyager to revert to the X-band transmitter and resume data collection. But the episode illustrated how thin the margins have become. The systems that kept this spacecraft alive for nearly 5 decades are operating in a regime where individual power management decisions can be the difference between continued science and extended blackout. Suzanne Dodd, Voyager project manager at JPL, he described the mission simply: "The Voyagers have been deep space rock stars since launch, and we want to keep it that way as long as possible." Patrick Coyne, the Voyager program scientist at NASA headquarters, offered the perspective that frames everything. The Voyager spacecraft have far surpassed their original mission to study the outer planets. Every bit of additional data we have gathered since then is not only valuable bonus science for heliophysics, but a testament to the exemplary engineering that has gone into the Voyagers, starting nearly 50 years ago and continuing to this day. When the last instrument goes dark, both spacecraft will continue outward. Nothing will stop them. They are moving through a near-perfect vacuum with no friction, no drag, no force capable of decelerating them on any human timescale. Or Voyager 1 will continue at approximately 17 kilometers per second, cooling slowly toward the 2.7 Kelvin temperature of the cosmic microwave background, the ambient temperature of the universe in the absence of any nearby heat source. Its circuits will freeze, its mechanisms will lock, its antennas will remain pointed in the direction of Earth, not because any program tells them to, but because no force will have acted to disturb their orientation. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. It will not slow down. It cannot slow down. It will drift through that star's gravitational neighbourhood and continue outward, and carrying the same momentum it has carried since Saturn's gravity flung it onto its interstellar trajectory in November of 1980. In approximately 40,000 years, Voyager 2 will come within roughly 1.7 light-years of another star, Ross 248, in the constellation Andromeda. Both spacecraft carry golden records. Each record is a 12-inch gold-plated copper disc mounted on the exterior of the spacecraft. On the record are greetings in 55 human languages, 90 minutes of music ranging from Johann Sebastian Bach to Chuck Berry to a Javanese gamelan to a Peruvian wedding song. There are sounds, a human heartbeat, waves on a shore, wind in trees, the call of a humpback whale, laughter. There are images encoded as analog audio, 115 photographs including diagrams of Earth position relative to 14 pulsars, a coordinate system intended to remain valid for hundreds of millions of years. There are instructions for how to play the record, rendered in a mathematical notation intended to be decipherable by any intelligence capable of building a device to receive a spacecraft. Carl Sagan, who chaired the committee that assembled the record, described it as a message in a bottle cast into the cosmic ocean. The records are exposed to the interstellar medium. Every moment since the heliopause crossing, the galactic cosmic rays that Voyager's own instruments measured and reported have been striking the record's surfaces. At the flux levels Voyager recorded, the gold plating provides some protection, but not indefinitely. Over tens of thousands of years, the continuous rain of high-energy particles will slowly erode the grooves that carry the audio information. The photographs encoded in analog form will degrade as the physical structure of the disk is gradually altered by radiation damage. The mathematical diagrams will persist longer than the audio. The pulsar map will likely remain readable after the music has been erased. The interstellar medium, hostile and indifferent, will erase the message. Not immediately, not violently, slowly over geological timescales through the same mechanism that makes the interstellar medium so inhospitable to biology, through the accumulated damage of higher energy particle impacts counted one by one over millennia. The voice of Earth, preserved with such care and such hope in 1977, and will gradually become noise and then silence. But before that erasure, something else was preserved. The data reached us, not the Golden Records data, which has not yet found a recipient and may never. The science data, the particle counts and field measurements and plasma densities and oscillation frequencies that Voyager's instruments gathered during the crossing and in the years since. That data is archived. It is published in peer-reviewed journals. It is available to any researcher with the curiosity to examine it. It describes something that no generation before ours had any direct evidence of. It describes the real physical conditions of the space beyond the sun's protection, not inferred, not modelled from assumptions, not estimated from the absorption spectra of distant starlight, but measured directly by instruments in contact with the medium. What it describes is this: the interstellar medium immediately beyond the heliopause has a plasma density of approximately 0.05 to 0.08 electrons per cubic centimetre, 40 times denser than the outer heliosheath. Its temperature is approximately 30,000 to 50,000 Kelvin, hot in terms of particle kinetic energy, but irrelevant as a heat source at such low density. Its magnetic field is approximately 0.3 to 0.5 nanotesla, galactic in origin and oriented differently from the solar field. It is permeated by galactic cosmic rays arriving from all directions at flux levels 2 to 3 times higher than the maximum ever observed inside the heliosphere, with lower energy particles present in abundances 5 to 10 times greater than inside the bubble. It hums with persistent plasma wave oscillations at roughly 2 to 3 kHz, a thin electromagnetic signal encoding the electron density of the medium, rising and falling slightly as local density fluctuations pass through the spacecraft's vicinity, and it extends with broadly similar properties for light years in every direction until the faint influence of another star begins to make itself felt in the particle counts and magnetic field direction. This is what the galaxy is made of, not the stars which are the exceptions. The interstellar medium is the rule, the vast dark cold, mildly turbulent, continuously irradiated medium that fills the space between every star and every other star is the dominant constituent of the galaxy by volume. And the stars are campfires scattered impossibly far apart in a wilderness that stretches 100,000 light years from edge to edge. The campfires are real and warm, but the wilderness is what most of the galaxy is. We live inside one of the campfires. We always have. Our species emerged inside a heliosphere. Our planet formed inside a heliosphere. The entire complex chain of biological evolution that produced everything from the first self-replicating molecule to the engineers at JPL who designed the instruments that crossed the heliopause. Every step of it happened inside the bubble. The bubble is the only environment our biology has ever known, the only environment our technology was designed for, the only environment, by definition, in which anything we know as complexity or life or civilization has ever had the opportunity to arise. Everything we have ever called home is a protected enclave, a small volume of space, shielded by a single star's continuous exhalation, inside a galaxy that is overwhelmingly composed of the hostile medium between stars. There is something that happens when you sit with this for long enough. Not fear exactly, not despair, something closer to a recalibration of perspective. The universe is vast, and most of it is not hospitable to what we are. But inside this specific bubble, maintained by this specific star, orbiting at this specific distance with this specific magnetosphere, and this specific atmosphere stacked beneath it. The conditions for complexity exist. They have existed for 4.5 billion years. They exist right now. And the heliosphere holds. The solar wind blows. The shield is up. That is not nothing. It is in fact the only reason the question of what lies beyond the bubble can be asked at all. Voyager 1 and Voyager 2 crossed the heliopause because they were built inside it, by people who lived inside it, using technology developed inside it, pointing instruments designed inside it at the medium outside it, and sending the results back across the boundary that separates one from the other. The crossing was made possible entirely by the conditions that the heliosphere provides. The instruments work because they were not degraded by the full galactic cosmic ray flux before they could reach the heliopause. The computers processed data because they were not fried by radiation on day one, and the solar-heated manufacturing environment that produced every component of both spacecraft exists because of the bubble. The Voyager mission is, in a very literal sense, the product of heliospheric protection using itself to measure its own edge and report on what lies beyond. That data is now in the archive. The measurements are made. The medium is characterized at least at one location, in one era, in one small region of one galaxy. Whether it is representative of the interstellar medium everywhere in the Milky Way, or everywhere in the universe, is a question that requires more measurements than 2 aging spacecraft can provide. But it is the best direct measurement we have, and it will remain the best direct measurement we have until something new is built and sent to the same place with better instruments and more power. As of early 2025, nothing is currently funded or under active development that would cross the heliopause within any near-term timeframe. New Horizons is heading outward and will reach the termination shock region in several decades, but its instruments were designed for different science, and its trajectory will not provide a direct comparison, crossing with the Voyager's locations. The Interstellar Mapping and Acceleration Probe, IMAP, was launched in 2025 to study the heliosphere's boundaries from within, using instruments designed to detect the energetic neutral atoms that escape from the heliosheath and carry information about conditions at the heliopause. IMAP will not cross the boundary itself. It will observe it from the inside. For now, 2 spacecraft with the combined computational power of a fraction of a modern smartphone are running on the slowly decaying heat of plutonium, sitting more than 15 billion miles from Earth, remain the entirety of humanity's direct presence in interstellar space. When they finally go quiet, we will have no instruments beyond the heliopause at all. The measurements will stop. The plasma hum will continue, recorded in its final datasets, referenced in the papers that analysed it, but no longer actively monitored. The medium will continue to press inward against the heliosphere. The heliosphere will continue to hold, inflated by the solar wind, maintaining the conditions that make the inner solar system the anomaly it is. And the galaxy will continue as it has for billions of years, mostly interstellar medium, mostly dark, mostly cold, mostly radiation, interrupted here and there by the rare warmth of a star, and the even rarer warmth of a planet orbiting close enough to stay liquid. There is something quietly extraordinary about the fact that we know this now. For the entire 4.5 billion year history of life on Earth, the boundary of the heliosphere was unknown. It was not unknown because no one cared. It was unknown because reaching it was impossible. There was no technology, no fuel, no trajectory optimization, no communication system capable of building, launching, navigating, and sustaining contact with a probe through to that distance. The heliopause could be theorized. It could be argued about. Models could be constructed and compared. But the real, measured, instrument-confirmed conditions beyond the boundary were inaccessible. Then in 1977, 2 spacecraft were launched on trajectories that would carry them there. For 35 years they travelled. And on August 25th, 2012, the boundary was crossed. The instruments registered what was on the other side. The data was encoded. It was transmitted at the speed of light, fading to 1/10 of a billionth of a trillionth of a watt by the time it reached the 70-meter dishes of the Deep Space Network, but recoverable, meaningful, full of information. Scientists decoded it and argued about it for 13 months, and then they announced it. We have been here. We know what is out there. We know the density and the temperature and the magnetic field strength and the cosmic ray flux and the plasma oscillation frequency and the turbulent spectrum of the local interstellar medium. We know the size and shape of the heliosphere with better precision than anyone alive in 1977 could have imagined knowing. We know that the bubble has collapsed before and that it will collapse again on geological timescales when the solar system encounters a sufficiently dense interstellar cloud. We know that the galaxy is mostly the medium and not the stars. We know that every star system is an island and the ocean between them is hostile. We know all of this because two machines, designed in the era of slide rules and magnetic tape, driven by the ambition and patience of teams of engineers who have spent their entire careers keeping them alive, crossed from the inside to the outside and that told us what they found. That is what Voyager actually did. Not just travel far. Measure the boundary of the only protective environment our species has ever known, and report back from the other side so that we could understand for the first time exactly how rare and specific and contingent the conditions for our existence actually are. The heliosphere holds tonight. It held last night. It will likely hold tomorrow. The sun is burning, the solar wind is blowing, and the bubble that has sheltered this planet through the entire history of life is intact. That is worth knowing. That is worth thinking about quietly, in the way that large things are best considered slowly and without rushing, with room enough for the scale of it to settle into something that feels real. The bubble holds, and beyond it the interstellar medium continues as it has for billions of years, quiet and harsh and vast, patient in the way that something with no awareness of time, no awareness of anything simply is, pressing inward against the boundary of every star's protection, filling the space between every fire and every other fire, everywhere in the galaxy, in all directions, to the limit of what measuring instruments built inside a single stellar bubble can presently detect. The data is in the archive. The machines are still out there, growing quieter by 4 watts per year. And the universe, as Voyager found it, is enormous and mostly dark, and occasionally in tiny protected islands maintained by ordinary burning stars, briefly and temporarily lit from the inside by something complicated enough to ask where it is. The asking itself is the most improbable thing in the picture. The heliosphere provides the conditions for biology. Biology provides the conditions for nervous systems. Nervous systems provide the conditions for perception and memory and language. Language provides the conditions for accumulated knowledge across generations. Accumulated knowledge provides the conditions for the mathematics that predicted the solar wind, the engineering that built the spacecraft, the orbital mechanics that threaded it through Jupiter and Saturn on gravitational assists, the communication and technology that sustained 47 years of signal across 15 billion miles, and the scientific analysis that confirmed what the instruments measured. All of that, from the first stirring of life in the early oceans to the engineers at JPL, who turned off the cosmic ray subsystem in February of 2025, and watched the confirmation come back 23 hours later. They happened inside the bubble, every step of it protected by a structure that no one could see, no one could feel, and no one knew with certainty existed until Voyager crossed it and reported from the other side. The heliosphere protected the asking of the question, and the answer the question received is that the asking is genuinely rare, the conditions are specific, the protection is conditional. The medium outside the bubble is real, measured and hostile. The nearest comparable shelter is more than 4 light years away through that medium. We are here. The bubble holds, and now we know with the precision of direct measurement exactly what we are inside of. That is the thing Voyager found, not just interstellar space, not just the heliopause, not just particle counts and plasma densities. The understanding that what we have is specific and earned by physics and not universal, and worth knowing about precisely and completely without flinching from what the numbers mean. The heliosphere holds tonight. Rest well inside it.